All right then, let's compute a simple example of flux. Let's say we have the simple rotational vector field F given by yi minus xj. This is a clockwise rotation. Very nice, very simple. And let's say that we compute the flux of this field along the straight line path that goes from a point on the y-axis with y-coordinate b to a point on the x-axis with x-coordinate a. Now, because of the way that orientation works in the plane, it sure looks like for positive values of a and b, this is going to have positive flux towards the end point at a comma 0 and negative flux towards the start point at 0 comma b. So what is this going to be? Maybe it's 0 because the positive and the negative cancels out. Well, maybe it depends on the precise value of these constants, a and b. Let's start off by parametrizing this straight line. Let's use the simple path given by gamma of t is at for x and b times quantity 1 minus t for y. Now, as t goes from 0 to 1, you can see that this works. When t is 0, I get the point 0, comma b. When t is 1, I get the point a, comma 0. We're also going to need the derivative, but this is simple. It is a constant. Gamma prime is given by a minus b. Now, to compute the flux along this path, I take the flux form, phi sub f, that is fx dy minus fy dx, and I integrate that along gamma. Substituting in, I get the one form x dx plus y dy. Now what I want to do is substitute in at for x and b times quantity 1 minus t for y. Substitute in those values for gamma. Substituting in a for dx and then negative b for dy gives me the integral as t goes from 0 to 1 of at times a plus b times 1 minus t times negative b. That, after some simplification, is quantity a squared plus b squared t minus b squared. Integrating that is going to give me 1/2 quantity a squared plus b squared t squared minus b squared t. As t goes from 0 to 1, we get a final answer of 1/2 times quantity a squared minus b squared. Now, does that make sense? Yes, it makes sense. I think it makes sense. Why does it make sense? Well, if a and b are equal, then the positive and the negative flux balances out because of the symmetry of this rotational field. On the other hand, if, let's say, a is 0 and I just have a vertical line, then I've got tons of negative flux going on. Whereas if b were 0 and I have a horizontal line, I have lots and lots of positive flux. This all makes sense. Okay, let's look at another example, a somewhat familiar example of a nonlinear spirally vector field. Do you remember this from earlier in the chapter? Minus y plus xy squared plus x cubed I plus x plus x squared y plus y cubed j, that vector field which spirals in a counterclockwise direction. Let's integrate that over that same radius r circle centered at the origin. But now what we have to integrate is the flux form phi sub f given by quantity minus y plus xy squared plus x cubed dy minus quantity x plus x squared y plus y cubed dx. Let's parameterize this loop the same way that we did before. Our cosine t, our sine t as t goes from 0 to 2 pi. And now when we integrate that flux form, what do we get? We substitute in x equals r cosine t, y equals r sine t, dx equals minus r sine t, and dy equals r cosine t. Integrate that guy from 0 to 2 pi and we get what? Well, we get a whole bunch of stuff. And not that much cancels. Just the first term from each of these two components of the integral cancels out. when we factor out an r to the fourth and look at what's left over, we get what? We get cosine squared t sine squared t plus sine to the fourth t from that first integral, and cosine squared sine squared t plus cosine to the fourth t from the second integral. However, with a little bit of factoring, we see that that is really just sine squared t plus cosine squared t quantity squared. And since sine squared plus cosine squared is 1, we get a simple integral of dt as t goes from 0 to 2 pi, all of that times r to the fourth, giving us a final answer of 2 pi r to the fourth. Now, this is different than what we got for circulation, but flux is measuring something else. When r is very small and we're near the origin, this vector field is close to a pure rotation, and so the flux is vanishing to fourth order. But when we have larger values of r and that vector field starts bending out, then we get lots and lots and lots of flux, and this flux is growing at fourth order in r. So as we compare what we've seen in this example between circulation and flux, as we think about the duality between these two, this is going to be increasingly important in what we wind up doing next. Make sure you get your flux forms and your circulation or work forms straight.